This video is on equilibrium. So the concept of an equilibrium, if you look at the word, obviously you see the word equal in there. So something in an equilibrium is equal. What's equal is the rate of a forward and reverse reactions. So chemical reactions run two ways. They run forward, like they have here in blue. That's left to right, the way we read. Some of them can be reversed. And when we have both directions happening at the same time, we have what's called an equilibrium. And if you look, we use a double arrow in both directions to show that these reactions go forwards and backwards. Now, in an equilibrium, the rates are equal, the amounts are constant. So be very careful there. The rate of the forward and the reverse are equal, not necessarily the amounts. Can the amounts be equal? Yes, but that would just be a coincidence. In most equilibriums, they're not. So equilibriums, and turns out you could have, if my reactants were chemical A and my products were chemical B, I could have 1% A and 99% B. That's like the most extreme example. But as long as every time at that point an A turns into a B converts back to an A, you're at equilibrium. It could also be the opposite way and you'll still be at an equilibrium. So the thing about the equilibrium, the rate is equal, but the percentages of, or the amounts of each one won't change. So if these are truly at equilibrium, they will stay 1 in 99 forever in either direction. Now, catalysts can affect equilibriums, or I should say them. They have an effect, but the end result is no effect. So catalysts have no effect on the amounts because, think of it, if every time an A converts to a B, let's say an A converts to a B every minute and then a B back to an A every minute, there's no change. All a catalyst is going to do is speed up the rate of conversion. So now let's say instead of taking a minute for an A to turn into a B, it takes a second. But it will also take 1 second for a B to turn back into an A. And so while they're moving faster forwards and backwards, the amounts of the products won't change because every 1 second an A will become a B and a B will become an A instead of once a minute. So a catalyst, they won't have an effect on the equilibrium, but they will make it reach equilibrium faster. Now, what it means to reach equilibrium. So it turns out when you do a chemical reaction, you could have a bunch of A, you could have very little or zero B. And so you mix the chemicals together initially and you're not at equilibrium, and then the chemical reaction happens. And then at some point, they reach a point where A and B convert equally. That's called reaching equilibrium. Now, in some chemical reactions, that can take a minute, it can take an hour, it could take a day. Every reaction's different. What a catalyst will do is it'll make it get to that point faster. But once at that point, it won't really do anything other than make the conversion happen quicker. But again, there'd be no net change that we would see. Okay, so that's the general equilibrium. Now, there's a couple different types of equilibrium, but they all share this one line in common. The rates are equal, the amounts are constant. That's the thing you have to keep remembering. So there's a couple ways to apply that. So we've got phase equilibrium. This can exist between solids and liquids. It could exist between liquids and gases. I guess in theory, it could exist between solids and gases if we were talking about an equilibrium between sublimation and deposition. I'm sure they exist, although incredibly rare. These are the common ones. So in a phase equilibrium, it would be when water and ice are converting into each other. So ice will be melting, water will be freezing. This actually can only happen, assuming STP, obviously standard temperature and pressure, this will only happen at 0 degrees Celsius. So at 0 C, we will have, you can have ice and water exist in equilibrium. So this is a common question that I ask a lot. If I had a glass of water and I put an ice cube in it, and I set my freezer to be exactly 0 degrees, and I put that glass of ice water into the freezer, and I came back a day later, what would I have? A lot of people think, well, it would be frozen, and that's because in your experience, your freezers aren't set to 0. They're actually set to be below 0 so that this doesn't happen. It really wouldn't be that useful if they were exactly 0. It turns out if I came back a day later, I would have the same ice cube and the same water, although it wouldn't be the same ice. Another example would be if I, made the ice with blue food coloring and I made the water with yellow food coloring and I put that glass of ice water into the freezer at 0 C, eventually everything would be green. Because what's happening is, it's not that they're sitting there doing nothing, that's what it looks like to us, but what's actually happening is the ice is melting, but every time a solid water molecule turns into a liquid water molecule turns back into solid. So basically every time the ice melts, it freezes again, and this constant conversion is what makes the equilibrium. And so there is something happening. It just, to us, doesn't look like anything's changing. On a heat and cooling curve, we'd be talking about this section right here, the part where you have HF and HS. Now you can do the same for phase. So for an example, would be boiling water. Obviously for boiling water, you would need to put a top on this because otherwise the steam would just, float away. So we're putting a top on, and it's the liquid gas equilibrium. And it's once you know one, you know them all. Every time a water molecule boils, it turns into a gas. That will cause a gas molecule to then condense back down into a liquid, and you have a constant thing there. And we see that all the time, like with cooking. The reason you can, like when you slow cook something, you can leave slow cookers alone. One, because they don't get too hot, but two, because they have that top. And so if you didn't have that top on them, eventually they'd evaporate all the water and you would have like a solid, dry, chunk of dried out meat or food or whatever you're cooking. So with the top, it allows the condensation part to happen. And again, heat and cooling curve, it doesn't have to be this particular direction, but we're talking about the top. We're talking about heat of vaporization and heat of condensation, this higher flat part on the heat and cooling curve. So that's phase equilibrium. There are two more types. There is solution equilibrium. In a solution equilibrium, it's the same idea, but now there's a couple requirements. So these things are required. You need to have a saturated solution. So just to recap, a saturated solution would be a solution that has the maximum amount of stuff dissolved in it. And we need to have that stuff, excess of it, so excess solute. So let me give you an example. I've got a glass of sugar water. This sugar water for this temperature and this amount of water is saturated. That means that I can't possibly dissolve any more sugar in the water. If I add extra sugar, it's just going to sit at the bottom and be excess. That's why we say excess solute. So you actually need both of those things to be true for this to happen. So now the water can't possibly hold any more sugar, yet I have a cube or block or scoop of sugar sitting at the bottom. So what's happening? Well, if you come back a day later, you make this solution, and you come back a day later, it's going to look like nothing happened, meaning that lump of solid sugar is just going to sit there and do nothing, but there is something actually happening. Turns out the sugars are dissolving, but every time a sugar molecule eventually gets into the water can't hold any more sugar molecules, so another sugar molecule is forced back out of the water, and it recrystallizes onto the solid cube. And so that is the rate of the solidification and dissolving are going to be equal. On paper, it would look like this. So on a Regents, they would expect you to see this. C6H12O6 solid, double arrow, that's the clue, C6H12O6AQ. And this one little line is telling me all of this, that the only way this can be true is these two requirements have to be met, and then this is what's going on. So that can be a little complicated. Last one, chemical equilibrium, otherwise known as Le Chatelier's principle. It is basically how chemical reactions can cause equilibriums. They're a little bit more complicated because chemical reactions, unfortunately, they move around. That's why equilibrium can be called, often is used the word dynamic is put in front of it. So we call these dynamic equilibriums. Technically, they're all dynamic because dynamic just means that they're moving. So although it looks stationary or static to us, there is movement going on, hence the term dynamic. Chemical reactions do this the most. So chemical reactions, we use what's called seesaw method. So seesaw method is literally saying that they are going to behave like a seesaw, and the seesaws are going to shift depending on what you do to them. Now, they shift to the side of the seesaw that goes up. So whichever side of the seesaw goes up is the side that we shift to. That's a fancy way of, that's a way of oversimplifying that the reaction is going to make more of that side. I'll get to pressure in a minute. So here's how it works. It's not hard, but you need to know how a seesaw works. So the first thing, you take your chemical reaction. The double arrow sign is the center of your seesaw. So here my double arrow should be exactly over here, but I guess I was off a little bit. It's a little bit better down here. So here's my chemical reaction. Think of it like this. So if this were my seesaw, there's my center. So what we are saying is if we do something to this. We assume that in the beginning, that even though they're not equal on both sides, we assume the seesaw is perfectly balanced. So then we say, well, what will happen? Well, it's very simple. If I add SiO2 to this chemical equation, just think, if I had a balanced seesaw and I add more SiO2 on the left side, well, what's going to happen to the left side? Well, the left side's going to go down because it's a seesaw. It will get heavier. The right side will go up. The seesaw would look like this when we're done. What that means is we're saying it will shift to the right because the right side went up. What does it mean in chemistry terms? It means the chemical reaction will make more of the stuff on the right and it will make less of the stuff on the left in order to rebalance the seesaw. That's what happens. So we would say it shifted to the right. Turns out there are 3 ways to make this chemical reaction shift to the right. We could add more SiO2. That would do it. We could add more O2. That would make it shift to the right. We can also take away SO3 because then the right side would get lighter and we would still shift to the right. That's how you shift to the right. Now let's look at shifting to the left. Shifting to the left means we do the exact opposite. If I add SO3, then the SO3 side gets heavier and the seesaw would do that. Okay, that's shifting to the left. The other way of doing it is to take away SO2 or O2, and that would make the left side lighter, which would also make it shift to the left. And again, if we shift to the left, it means the chemical reaction will make more of the things on the left, less of the things on the right, and the purpose is to rebalance or reestablish equilibrium. I will explain more about shifts in the first worksheet, which is why they are important. And the last part is pressure. So pressure will only affect gases. So if you don't have gases in a reaction, then pressure will have no effect. If you have equal amounts of moles of gases on either side, pressure will have no effect. In this reaction, turns out there's not an equal amount of gases. We have 2 moles of SO3 gas. So the only thing I care about is that there's 2 moles of gas on the left. The formula doesn't matter. And I have an unwritten 1 here plus 2 more over here. So I have 3 moles of gas on the left side. So if I increase pressure, I shift to the side with less gas particles. So if you increase pressure, you would shift to the right. It would go this way. And decreased pressure would cause this. As far as the actual reasoning behind why these shifts occur, turns out it's really more about collision theory, and by introducing more particles, you will have certain collisions will be more likely and other collisions won't, and therefore you will make more of one direction or the other. So it's really collision theory that's guiding this, but it actually is it's a little bit more complicated to explain it that way. So we are using an analogy of a seesaw and a shift to really explain what's happening with which collisions become more statistically likely over time. That's really that's what's really driving this. In our next video, I will have the worksheets and I'll explain practical problems. I'll go through a couple sets with you and there will be answer keys for this.